All right. Hi, everyone. Thanks for joining us today. As we said previously, this is very informal, as you can see. So, what are you drinking, Serena? I'm drinking tea and honey and lemon.
I also have some tea in this French press.
Ooh, tea and French press. That's
I
a
know.
bit extreme.
Yeah, I bought this French press like probably 10 years ago, more than 10 years ago when I worked at Starbucks. I remember
Mm.
all the rage was the Bodum French press, and I wanted one because I was young and impressionable back then.
Well, we all have our own ways of drinking tea, let's say.
Yes.
Awesome. So, today we're going to talk about deep random walks. Um, I know both of us researched a little and found a few resources and wrote some notes. For those of you who are joining us today, I'm sharing the notes on a screen. And I know the layout is a little weird because of the software you're using, but um, the goal is to share this with you later so that you can go in through this as much as you want. Um, One of the things that I wanted to say is that, since this is very informal, there will be a lot of places where we don't know the answer to a lot of questions that we ask ourselves or you might ask us. And that's where we need your help. So occasionally we might say something that is incorrect. So if you know the right answer or the right thing to say, instead, write it in the chat, either in the live chat if you're watching during the stream, or later as a comment on the video, so that we can, go back and fix our notes before we publish it, or after we publish it, doesn't matter. But also sometimes, there might be, and if you're saying something, ideally, provide the resource that supports what you're saying rather than just saying something, because then that would
Yes,
be
tell
harder.
us why.
Exactly. Like, if say something and say this is a good resource to learn more about it. And sometimes there are some things that we didn't have time to look at. So we might just bring it up and ask you to help us find a resource that, answers that question. And again, like put it in the chat or on the comments later. Uh,
Mhm.
Hopefully later we will make this a little easier for you to do very quickly. But for now, we're going to do a little manually and see eventually what happens. What do you
And
think?
yeah, yeah, I just want to say, as you said, Amir, we are two machine learning enthusiasts, especially this particular topic, graph neural networks. I'm not an expert. I feel, Amir, that you have a bit more expertise here because you've spent more time with it. Okay, so you're shaking your head. Yeah, like we kind of don't really know what we're talking about. So feel free to correct us. And that's the only way we can really learn if people tell us when we're wrong. And
Definitely.
speaking of being wrong, Amir, I wanted to talk a little bit about the title of this YouTube show and the
Okay.
inspiration for it, because I think it does tie into, well, random walks and deep learning. And I had posted on LinkedIn saying, hey, everybody, here's our new YouTube talk show. It's based off of, it's called Deep Random Walks, which is a play on deep learning and random walks, or the random walk. And I think you messaged me on Slack saying, hey, it's actually based on this particular GitHub repo or paper. But I disagree. So I just wanted to talk a little bit about, and maybe it would be fun for people to hear
Hmm.
our thoughts on this. So I think that the paper Deep Random Walk itself is a play on deep learning and the random walk. And given that I did work in finance for the past like 2 years or so, and previously as well, I kind of care about the random walk. So I want to talk about it a bit. And you
Yeah.
could scroll down on the resource notes. That's so like the folks who are watching can see a bit about what I'm going to talk about. Okay, so I guess, Amir, how familiar are you with the concept of a random walk?
So being a physicist, I've played with random walks a bit. I have some thoughts around the importance of random walks for sampling as well.
Mm-hmm.
But I'm very curious to hear your thoughts and the finance angle that you started talking about.
Yeah, I guess like essentially a random walk, for anybody who might not be familiar, is you start at a particular state or a particular position and you can move to like state one or state -1 with equal probabilities. So that's why it's random. I remember I had a professor, Dr. Andrew Hendry, shout out to him at McGill. I think he taught like Bio 111. and he told us about the random walk in the context of biology. And he did it by pretending to be a drunk man walking home. And as like young university students who like to party, we all really empathized with that. Most anyways. So he would say, you just be like, it's like you're walking and you just like randomly go over here, then you randomly go over there anyways. And that like really was the first time that I encountered the concept of the random walk. And then I forgot to put this in the notes on our end, but maybe you can add that, Amir, as I'm saying. So apparently the random walk was first introduced by Carl Pearson, the statistician, I think in 1905. So we love him not only for Pearson correlation, but also for introducing the random walk. And yeah, like I said, people love and as you can see in the notes, everybody, so people in finance love the random walk. It's a very popular concept. It was popularized in this book called A Random Walk Down Wall Street. It came out in, again, I have these notes on my end, came out in 1973, and I think it sold over 1.5 million copies as of 2020, something like that. So it's very popular. And it popularized this phenomena that is a bit controversial, actually, called the efficient market hypothesis. And essentially, the efficient market hypothesis says that anything that can contribute to stock price is already priced into the market. The market is fully efficient. Therefore, any change in price is actually random. However, that this sort of concept of random walk and efficient market hypothesis, there's a bit of contention there. So some economists say that if the market is efficient, well, the market can't be random, because if it's efficient, it's not random, that sort of thing. Really, people don't disagree, but yeah, having worked in the space, I can say that random walk applies to the stock market in the sense that it's just very difficult to actually predict stock price because things are random. So all that being said, that's why when you said that the name of the show is Deep Random Talks, I thought about the random walk in the context of finance right away, because that's just like the world that I've come from. And of course, deep learning comes into play as well. So that's my piece on finance.
Sounds good. So maybe one clarification, because I don't remember all the assumptions in random walks. So I'll talk a little more about it in the context of graphs, but so random walks are essentially ways to sample a distribution that exists. So did you say that these distributions, there are some independence assumptions about them?
I think I didn't mention that, but there are independence assumptions, right?
Okay. So the independence is basically like, what are the things that are independent? Like, are we talking about events or
yeah,
clarify that a little?
Yeah, it should be like the price at time t is independent of the price at t minus 1 and t minus n. So like the only thing that impacts the next price is like where we are currently, because you'll either go up by some quantity or down by some quantity. Yeah.
Which is the Markov assumption, right?
Yeah,
so
exactly.
Essentially, every step is only dependent on the previous step.
Mm-hmm.
I see.
Okay. Which is so cool. Yeah, I loved learning about Markov chains.
Yeah, definitely. Okay, very interesting. So I guess that's one of the very first observations that I had when I started looking at random walks, and especially their applications on graphs, is what I wrote on the top, that since the rise of social media, the number of papers that I saw about trying to analyze graphs significantly increased. That's very anecdotal, and I didn't really look at any trends or anything, but I bet there is something significant there. And I assume part of it is because all of a sudden data sets from social media became available that essentially are graph-like. And people started thinking about different ways that they can, obviously, if you have a graphical data set, it's going to be difficult to analyze it as a graph data set. So because it could be too large or the complexity could be too much. So usually, I guess the goal is to look at the linear sections, like zoom in so much that it almost looks linear, or the structure is simpler, and sample a lot of things like that, so that you get a population that represents the actual data set, and then use that to do your statistical analysis, or later other types of analysis that you would do with deep learning and such. But it was very interesting for me to see that essentially, I think I found this paper called Practical Recommendations on Crawling Online Social Networks, which analyzes a bunch of different ways that people use to essentially sample graphical data sets. One technique being, random walk based, and there are other techniques that they call them breadth first or depth first ways. I think the difference, as far as I understood, is that random walks just essentially randomly sample these graphs, but the breadth first or depth first try to do it systematically. So if they look at one node, they don't look at it again, etc.
Yeah, maybe I can jump in.
Please
this
do.
reminds me of when I was prepping for interviews and doing LEET code and a lot of like software engineering stuff. So yeah, depth first search and breadth first search, they're very systematic, like you said, and very rigid in a sense of like how they work. So depth first search is given some sort of like graph structure or tree. So well, a tree is a graph, some sort of graph structure. You want to visit every node in a particular path or in a particular branch first. So like if you have your node and there's a bunch of neighbors, you don't care to explore the neighbors. You just go through that entire path. And with depth first search, there's like pre-order, post-order, in-order traversal. So again, very systematic. Pre-order is like you visit the current node first, then you visit the left node, then the right node. I think post-order is you visit the left, then right, then current node. In order is you visit, I think, the left, current, and then the right node in this systematic way until you've traversed the entire tree. Breadth first search is more like you visit a given node's neighbors first. And then as I was preparing for this, I was kind of thinking about like the different applications of when you would want to use random walk versus breadth first search versus depth first search. And I guess what I was thinking of is like, if you have a social network, Facebook, for example, maybe I might want to ask like, hey, Amir, do you know anybody who lives in Sweden? And I think an algorithm for that could be depth first search under the assumption that people in Sweden are located far away from your like initial core group of friends on the social network. And then breadth first search, I couldn't really come up with a good example off the top of my head. I was just thinking like, well, I'm from Vancouver, so maybe a question might be, hey, Serena, let's find out who you know from a suburb of Vancouver. So maybe breadth first search would make sense because it's more likely that I'll have people in my immediate circle who live in that area. I don't know. Can you think of any like applications or like what I said? Did that kind of make sense?
Nothing immediately comes to mind, so that's a good place for the audience. If
That's true,
you know
yeah.
examples, please write it in the chat with a link, ideally, so that we can add it to the show notes. But I think the interesting thing about all of these different methods for me, Serena, was that ultimately the goal of any of these is to get a uniform and unbiased sample of the population. And I'm not sure if it was this paper or the one that I'll show next. It was very in depth about how these different methods introduce a lot of bias. And one of the interesting things that I saw, and we'll get to it later, is that the techniques that are not random walk based, like both random walks and other techniques, are prone to bias towards nodes with higher what do you call it? Higher degree.
Yeah, higher degrees, like higher number of connections attached to it. Yeah.
Right. So there is a bias towards them, obviously, because there are more ways that you can get to them. But apparently, it is easier to correct that for random walks versus other methods, and that's why they're more popular in sampling graphical data sets.
Do you know how they do that? Is it by like assigning a different like transition probability based on the tree? Something?
I guess we can just scroll down there right now. So this is essentially what I just said. There are two different ways to, in a classical sense, like not in deep learning methods. There are two ways that you can sample graphs. I guess in deep learning it might be relevant too. Anyway, so either you traverse the graph, like either the breadth first or depth first. So you're just traversing the graph. You're not doing a random walk. You're systematically going through it to get samples of this graphical data set, to do a statistical analysis on it, blah, blah, blah. And, the bullet points that are shown here are examples of that, breadth, the forest fire and a snowball. I didn't look at them, but you can guess what they are.
I can't actually.
Oh, forest fire.
Well, I guess I have an idea. But
yeah, I didn't look into it, but I assume it is some sort of a percolation where you start somewhere and it just spread all over the graph, I assume.
Yeah, and maybe snowball sampling has some sort of like speed parameter, like
Could
I don't
be,
know.
yeah. Anyway, I guess for the sufficiently curious people,
let
you
us
can
know
look
what
it up.
those two things are.
Yeah, and send us links for the best links you find for any of these. That would be very helpful, and we'll add it to this. And the random walk based ones have this major problem with the degree of the nodes, like that creates bias. But these are a bunch of ways that they can be fixed. So essentially, you can reweight your random walk. Like you do the random walk, get a bunch of results, and I assume you normalize it by the degree of the node or something like that, for example. There are the random walks with jumps. I didn't go too deeply into it, but et cetera, et cetera. So weighted random walks, as you said, is definitely one of the ways people deal with this. And yeah, that was definitely very interesting. And a lot of the papers that I saw were all about comparing different methods in different scenarios for how you get rid of this bias to get that uniform distribution. So let me see if I missed anything from the top. But ultimately, your goal is to get a sampling of the data that is representative of the population. It is uniform, so it covers all the subgroups of the population, and is unbiased, so it doesn't look at certain nodes more than others. And of course, like all statistical methods, your goal is to get a small sample and then draw conclusions about your population. We talked about these different ways. That paper that I just talked about, I quote, said that this survey paper, Random Walks on Graphs, a survey, is an excellent overview of everything about random walks on a graph. So again, for sufficiently interested folks, you can read this. This is 38 pages, but you can skim it and pick what you want. So we talked a lot about the statistical methods that we would use on graphical data sets to get a sample, to do statistics, blah, blah, blah. But going back to what this session was supposed to be about, deep walks, what did you find about that?
Yeah, so with deep walk, I am just scrolling through the notes. Well, so I went and directly looked at the deep walk paper, but I also was wondering if we should maybe talk about node to vec as well, because I feel that I'm going to bring it up. So I wanted to talk about node to vec because I know that node to vec is very popular, sort of like with recommender systems, the first algorithm that people often implement, other than like some sort of simple matrix factorization, is like alternating least squares, which is what Netflix used, like the Netflix prize paper in like 2014. I don't know. That's kind of like what everybody uses. I think node to vec seems to be the algorithm the industry uses their like first kind of like foray into graph neural networks or graphical problems. So then I was looking up before this session, what does node to vec actually do? And it seems like node to vec is very similar to deep walk, in that deep walk, it uses a random walk to learn, like, I guess, sample around a particular node and get some distribution. Node to vec uses a weighted random walk where there's like two different parameters like Q and P, and I'm not sure where they are applied, but apparently according to this Medium article or towards data science, the parameter P prioritizes breadth first search and the parameter Q prioritizes depth first search. So I don't know if maybe they're equal, maybe that results in a random walk. And then that just makes me think like there's this term random walk used all the time, but at what point does it become not a random walk and it's something else, and maybe we should not use that terminology anymore? And I think that's like the purest finance person in me coming in and saying like, let's not abuse terminology in that sense. But I guess I'm curious if anybody has used Node to Vec and has opinions on what parameter values to set and like what seems to work best, like depth first search, breadth first search. I would be pretty curious about that. And then I guess coming back to Deep Walk, so comparing it to Node to Vec, like I said, it seems like Deep Walk uses a true random walk instead of a systematic graph traversal method. And yeah, so according to the GitHub repo, which you can see here in the notes, so random walk uses short random walks to learn representations for vertices in a graph. And I guess to summarize it, it seems like given a node, Deep Walk traverses the node, and every step in that graph can be treated like a word in Word to Vec. And this is getting a bit into the weeds a little bit, so feel free to correct me or stop me, Amir, at any point. But essentially, Deep Walk says, like, how can we apply Word to Vec to graphs? So in order to apply Word to Vec, you need some sort of sentence or something that looks like a sentence, some sort of sequence, really. How Deep Walk does this is by doing this random walk on a graph. It gets these sentences, which are just sequences, and then applies Word to Vec. So I think that's a very cool way of doing things because, you know, I think if you can simplify a more complicated problem and use a method that you're familiar with, I think it's a good approach. So that's pretty much my takeaway from Deep Walk. Like, it uses Word to Vec.
Okay. I was under the assumption that that's what Node to Vec was. So what's the difference then? Because I assume Node to Vec uses a random walk to create the sequence samples, and then uses a Word to Vec like algo to turn them into vectors.
Yeah.
Is that the case?
I think it's the sampling method that differs. So that random walk, I think, and again, everybody in the audience, please correct me or us, because we could both be wrong. I think that Deep Walk uses like a traditional random walk, and maybe the length of the random walk differs, whereas Node to Vec uses a weighted random walk, or perhaps not even just a random walk. It like either uses breadth first search or depth first search, but it's really that sampling method that differs. But then like the actual process of learning the vector representations, I think, is the same, in that they both use Node or Word to Vec.
Mm-hmm. Okay, so I guess our current understanding, and again, somebody who might know better might correct us. Our current understanding is that Deep Walk is based on essentially an unbiased and actually random sampling of the graphical data, but Node to Vec has bias parameters that could bias it towards, do it random, but look at the prioritize going, in the breadths rather than the depth first sort of thing. Okay, interesting.
That's right. Yeah, and then just to continue talking over you, one other point I really liked in terms of like implementation in industry, I guess, is that the authors of Deep Walk say that it's parallelizable, because if you do multiple local short random walks in different parts of a graph, then you can compute all of those at the same time. And another interesting point was if the algorithm is focusing on local exploration, like any differences in the graph structure far away, in terms of like path length far away from a particular node of interest, like that node's representation is insulated from the effects of or changes like far away from it, which is also a cool attribute, because with machine learning modeling, I still, like in practice, I haven't really figured this out. Like, how often do you need to recompute your representations if you're getting new information coming in?
Right.
I don't know. So this is like a solution to that potentially.
Yeah. I mean, my rule of thumb is 80-20.
Yeah.
If the delta, I guess that's a very rough way to do it, obviously. But if the delta in your, like, obviously you can recompute the embeddings with every new data that is coming in. So at least you get embeddings for those based on essentially, if you're doing, I guess what they call an inductive embedding method, it is able to produce embeddings for the new nodes that you're adding, right? So as the data is coming, you can just keep producing embeddings for them. But at some point, if the amount of the new data points that are added is large enough, I assume the structure might change significantly. And I'm just throwing out 20%, so it is changing some metric by 20%. Then you might want to retrain the whole network from scratch so that your induction becomes better. Again, like, I'm just waving my hands in the air and making that argument, but that's an interesting segue to the next part that I found, that there are some methods that are transductive, which means that they're not capable of predicting the embeddings for the new data points that you're adding. I didn't go deeper to see what methods are inductive and what methods are not inductive, but that was an interesting point as well.
That's interesting. And I'm just thinking, like, yeah, when would you want it to be transductive? When would you want it to be inductive? Because I guess I can add from like my finance background that like the financial market space is very interesting because it is very difficult to predict any movement in stock price. But what I would say is easy is that if you're not doing high frequency trading where like updating your representations to the like microsecond or whatever actually matters, there's very specific times at which you want to update your models. Like if you're trading every 2 weeks, you don't really need to update your models every single day. And for that reason, that's why I'm like, I actually have no idea how to do or how to know when you would want transductive versus inductive modeling. So again, if anybody in the chat or anybody watching this knows, let us know.
Yeah, I assume there are also time complexity implications in either of these. So I assume that transductive methods are cheaper to run computationally, but that's my assumption. But I think you would use transductive methods, assuming that they're cheaper to run, only if your data is not changing a lot. So what you care about is, I have a large data set, and all I care about is neighborhood mining. I just want to find communities in this data set. Or generally, as I wrote there, descriptive type of task. You want to do clustering, et cetera, et cetera. Like, there's nothing about, there are nodes being added to this, or I want to, predict lengths or things like that potentially. I just want to analyze the existing graph and tell you the properties of it. Like in those cases, and I guess that's conditional on the fact that the graph is not changing very rapidly. If it is, I think you can do that for 5 minutes. Then what? All right. So I guess what I'm trying to say is that it really depends on the use case, I suppose, and what kind of information you're interested in, as well as essentially the update rate of your data set.
Yeah, that makes sense.
Could be. You're just guessing.
That's right.
So obviously, a lot of things we do end up being a rabbit hole. So as I was reading about these things, I started wondering what are all types of graph embedding methods that people use. And I came across this Medium article. I'm just going to be honest, I didn't really read any of the things that I'm suggesting. I just skimmed it and found a bunch of interesting points from them, including this one. The interesting points from this article were the fact that there are two ways to look at different embeddings methods. One is embedding methods that just produce embeddings for nodes. So you don't particularly care about the property. Sorry, you do, in all cases, you care about the properties of the graph. But in one case, you just care about getting a vector for each node. So for example, all sorts of word embeddings are like that. The word that you have, or a token in general, is a node, and all you want is a vector for that. Now, if in a slightly different scenario, if for whatever reason you want an embedding for a neighborhood, then you need a graph embedding method. And it is not necessarily as trivial as grabbing the node embeddings and averaging them, for example. I mean, that's a trivial way that you can do version 0.01, but you can do better. So graph2vec was another example of graph embedding. I didn't find anything else mentioned in that article, but if anybody knows other graph embedding methods, I believe GNNs do a bunch of that. But
yeah, I was going to ask, and like graph convolutional networks, is that gets you graph representations rather than node representations? I wish we had Korean here.
I know. I literally have that question at the end.
Okay,
So
nice.
do GNNs produce node or graph embedding or both? And I guess GNN is very, very wide, so it is probably hard to generalize, but we'll hopefully one of you will send us a resource that explains that, or otherwise we'll try to find the answer to that and add it to this document before we publish it. But the techniques that I found were this list essentially. So matrix factorization, I guess, is the most classical way to do graph or node embedding. I guess it is mostly for node embedding. And it is essentially grabbing the adjacency matrix and factorizing it, right? Like you do in recommendations. Is that the idea?
That's what my thinking would be about how to use matrix factorization for graphs. Yeah.
Okay. So because in recommendation systems you have items and people, which is sort of an adjacency matrix, and your goal is to get embeddings for people and get embeddings for items, and then multiply them, blah blah blah. And then you can layer more complex things on top of that. But the very basic idea is to get a representation for the item or representation for the person, for the user.
Yeah, exactly. And as you mentioned, recommender systems, it made me think. I actually came across Deep Walk for the first time when I was doing some research for some of the Rexus work with my research group. And thinking of it now, like pretty much, okay, this is a very broad statement, but I'm going to say any problem can be represented as a graph, perhaps. I could be wrong. But also any graph problem, I feel, can be represented as a natural language processing problem because it's a sequential problem. And that's what I sort of found when I was doing this research for Rexus, that anytime I found a graph method, it was then seemed to be unrolling the graph into this sequence and then applying something like word2vec, or applying maybe something a bit more complicated like a transformer or whatever. But I find that very fascinating, just how all of these methods are so connected. So even though I am a machine learning enthusiast who doesn't know very much about graphs, it suddenly, my knowledge of like NLP, for example, makes graphs feel a bit more accessible, but I still have no clue what I'm talking about.
Yeah, I think that's a very interesting point, because I think, again, like, I don't know about machine learning as deeply as I should, but I think generally speaking, historically, we are good at handling sequential data, because back in the day, we probably wanted to analyze a lot of time series kind of data. And then later, when NLP became a more important thing, we developed a lot of techniques to deal with sequential data that natural language is. So we got really good at these kind of things. And we are essentially, for good or bad, using them as hammers. So if we have any sort of data set of any shape, that we can turn it into sequential data and then use those hammers on them. And I'm not saying that that's a bad thing. Like, it works in a lot of cases, and at least it is a good first attempt in in our initial attempt at figuring out more advanced methods. But yeah, definitely, like, grab an arbitrary thing, turn it into a sequential thing, and apply the normal tools that you have on it to see what you get. If it makes sense, great. Just start using it.
Yes, I like that hammer a lot.
Yeah. I mean, some hammers are really good. They work for many types of nails. So, anywho, so Deep Walk, and I added these two that were not mentioned in the article, but I know from the previous talks that we have done, these are two types of neural network-based methods to deal with graphs. Again, I don't know enough to talk about them, so I leave it to the audience. One of the interesting things that this article talked about, and I think you sort of alluded to, is the time complexity of these algorithms. And generally speaking, one of the most challenging parts of using graph as a data source is that doing computation on it is very expensive. And especially, depending on the technique you're using, it could have very, very different consequences for what kind of data set you can deal with and what kind of inferences you can do, etc. So that was interesting that the article it didn't go into any sort of detail, but it just mentioned the time complexity of some algorithms. And it was interesting for me to see, and again, like I didn't go into depth, but some algorithms are more sensitive to number of edges versus others that are more sensitive to number of nodes, etc., etc. And I think that's also a bit of a difference between different methods that you're using, and probably the quality of representations they produce.
That definitely makes sense. And I guess the space complexity for all these sorts of graph algorithms would be the same, because I assume that you're working with the same adjacency matrix, but just essentially you're traversing in a different way and then learning different representations. I guess like some algorithms might copy the adjacency matrix, so then that would like double the amount of space used. But yeah, that's a very interesting point about time complexity. I never really cared about time complexity or space complexity or any of that stuff until I was put into a position where the cost of computation could be directly pointed to me and the ML work that I was doing. So I'm now very sensitive to this. So it does seem like, so if what is LLE?
Laplace something.
Okay, something Laplace.
Yeah.
So that runs in O of edge times D squared. So number of edges times
embedding size.
Embedding dimension. Okay, nice. And then deep walk is O of the number of nodes times D. So deep walk would be better, assuming that, every edge or every node is going to have multiple edges. Okay. So I guess in this case, it's like deep walk would be better for time complexity, but maybe the accuracy wouldn't be as high.
Yeah, I mean, that's sort of what you would guess.
Yeah.
Like the number of edges generally are significantly higher than the number of nodes. I guess in a fully connected network, they could be as many as V squared, right?
Right.
Most networks aren't. But yeah, definitely V will, in most networks, will be smaller than E. And D is the same, but LLE scales as D squared, which is definitely worse.
Yeah. And apparently, now I'm trying to find out the time complexity of node to vec in as fast as I can.
Okay, while you do that, I'll talk briefly about another article that I found on towards data science. It repeated a lot of the things that we've talked about so far, but I think it mentioned three major challenges that you have to take into account when you're using graph embeddings. So one is, making sure that whatever embedding method you're using captures the property of the network that is relevant to use case you're doing. So, for example, if the structure of the network is super important, you want to make sure you're using an embedding method that captures that as genuinely as possible. The second thing was, the wording of what the person said, the size of the network should not decrease the speed of the embedding. I think that's the case. It will, as you saw in the time complexities. But I guess what you're hoping to achieve is that it doesn't scale too bad. Linear might be okay, but if you can get sublinear, even better, etc. But if it is like a square of the size of the network, you're probably in trouble.
Fuck.
especially if the size of the network, I assume, is the number of edges.
Yeah, and if the network is very densely connected, I found the answer for node to vec. You should
Okay.
not be using node to vec. So apparently there's some sort of branching factor. I'm not sure what a graph's branching factor is. Maybe Amir, you know, but node to vec is O of b squared, where b is the branching factor. So this paper that talks about efficient graph representation says don't use node to vec if your network is densely connected. So there you go. I added that to the notes.
Okay, perfect. And right, and the last point is the dimensionality of the embedding. So obviously, as we saw in the time complexities, the dimensionality comes in directly, either as a squared in these two examples or linear. And again, that can have a significant impact on the time complexity of what you're doing. Of course, we have to do a plug. We have a package on graph neural networks to get essentially called Getting Started with Graph Neural Networks. Again, the link will be available. You can look at it. Our very good friend Karim has created a bunch of videos explaining a lot of the things that Serena and I are just fumbling through in a much more educated way that you can learn from him. And this package also has a bunch of hands-on components, so you can pick them up and learn from them, etc. And there was a survey paper that went through essentially categorizing a lot of different techniques and comparing them, and look at a lot of the things that we are talking about, but in more systematic way to just compare them and analyze them. I don't think we need to go into too much detail of that. I didn't look at it, so I don't have much to say. But we'll provide this link for you to take a look at. And what I didn't find a lot of time to do was to look further into details of GNNs in general and understand better what different flavors of GNNs are and what their advantages and disadvantages are. But I think that's an interesting thing to add to this conversation.
Definitely. I think another interesting thing to add would be graph expert. That would have been fun, but this has still been good to build our understanding together.
Definitely. Awesome. Thank you for doing this with me, Serena.
Welcome. Thanks for having me.
Let's see if you have any questions from the chat. I don't see, there are a lot of comments and conversations, so that's great.
Are you looking at the YouTube?
Yeah, I'm looking at
mostly YouTube. Me and Miriam. Miriam did share some examples of breadth first search and depth first search. Okay. In practice, maybe I can share it here. So shortest path. Yeah, sure. So Miriam said shortest path and minimum spanning tree for unweighted graph. I'm going to guess that is breadth first search, an application of breadth first search. Miriam, correct me if I'm wrong. Peer-to-peer networks, perhaps depth first search, and crawlers and search engines. I'm going to guess that that's depth first search. Anyways, interesting stuff.
We need also good definitions of what breadth is versus depth.
Yeah.
Because I'm not. Yeah, I think we just waved our hands through that part, but.
Yeah, anyway. if you think of like a tree representation that has like a node and then different levels and different branches, like breadth first search is you traverse a level.
Right.
Whereas depth first search is you traverse a branch first.
Right.
So there's your definition.
No, I understand, but
okay.
typical graph is not a tree, right?
I know, that's the tough thing, right? And I learned it. I learned this through tree representations.
Right.
And it's like it's a bit of a jump to think about it in terms of a graph. So yeah, it's a good point. If anybody knows, let us know.
Yeah, because I understand it for the search problem specifically, because in search problem, normally the way you make efficient, like most efficient search algorithms, create this index hierarchy where sort of like, bigger clusters are indexed closer to each other, and then you find your right cluster and go to that, and then sort of like, as you said, like you instead of going depth first or breadth first, you just go by bigger cluster and then the lower clusters, and you just go down. And that's how you get sublinear search performance normally. In that context, I get it. But for a typical graph that doesn't look like a tree, then what is the depth and what is the breadth? Oh, yeah. Anyway.
Yeah. We got one more question from Induction Hypothesis. Hello, Induction Hypothesis. So Induction Hypothesis is wondering what kinds of theoretical questions should be urgently answered, in our opinions.
Ooh, interesting. Well, you go first.
I was going to say, as the physicist, I feel that you are closer to theory than I am.
I mean, there are a lot of interesting science questions that are being answered through applications of graph. So, AlphaFold is a very good example where they try to use graph-based methods along with other things to essentially figure out how proteins fold and all that. Again, like I don't know a lot of the details, but I know that graphs are being used significantly in science-based applications of machine learning. In terms of the graph theory itself, actually, I don't know much. But one of the things that we are researching and we are very interested in is efficient in terms of time complexity ways to cluster an arbitrary graph into neighborhoods that essentially doing hierarchical clustering on a graph dataset, because that would essentially make a very interesting way to navigate these graphs. So if you start on an arbitrary point on the graph, normally if you try to look at all the graph, that's very overwhelming. So we are very interested to know, if I give you a node on a graph, can you give me a reasonable sized neighborhood of that node that I should look at? And then if I want to go one abstraction layer higher, which is not directly represented in the data, like it's not a tree data set, it's a graph data set, how to do that efficiently, how to essentially zoom out and see one layer of abstraction based on hierarchical clustering, et cetera, et cetera. That's a very, very interesting problem that we are researching and hoping to find an answer with our collaborators at McGill. That's the only big thing that comes to mind. Like, I don't know enough to know what other questions are important.
Yeah, same here. I can say in general in terms of... Oh, sorry, go ahead.
No, I just wanted to say transformers on graphs.
Yeah, is that being done already? That just sounds so computationally inefficient.
Oh, yeah, okay.
Yeah. Induction Hypothesis says, thank you for your answers. Yeah, I guess one last thing this is general machine learning and representation learning. I would love a theoretical, I guess I'm going to say framework. Framework's probably a bit of overload, but what dimension should my embeddings be? That's something that I always am not sure of. I came across a heuristic that says like the fourth root of the number of items or entities in your data set is a good starting place. But I've never really been able to figure that out. And I use that heuristic and kind of like, adjust from there. If anybody knows, let us know. And Miriam,
do you have a resource for that?
Yeah, it was some sort of Google article about transformers, I think, that said that.
Okay.
Miriam is saying breadth first search uses a queue data structure for finding the shortest path. Depth first search uses a stack. Okay, this brings me back to LeetCode code days. Breadth first search can be used to find the single source shortest path in an unweighted graph, because in BFS we reach a vertex with the minimum number of edges from a source vertex. Thank you, Miriam. Can you implement this for us?
There you go.
Miriam's like, no, I have too much other stuff to do.
Yes, definitely. As you were talking about the thing that you would like to see, and again, going back to my physics days, one of the other interesting things, and I think it is also very relevant to the work that we are doing at Aggregate Intellect now, but very different setting and use case. I've been seeing a lot more work on physics-aware embeddings. So essentially, embeddings that are not just based on the data set itself, but also from known symmetries that we know from physical theories. Because just trying to learn from the data set alone is not going to be super efficient. So, graph data sets represent the specific topologies, and a lot of the graph embedding methods are trying to learn those topologies on their own based on the data alone. And a lot of time they get it wrong because obviously we are using a sample, not the overall, not the infinite population that is necessary. So people have started embedding, well, that's a pun, but people have started integrating physical intuitions through symmetries that we know about systems into ways that we train models to get embeddings, to be able to get embeddings that are more aware of the physics that governs the data set that you're working with. That's also very, very interesting.
That's super cool. I would love to cover that in one of these talks if we can.
I actually know somebody who works on that topic.
Okay.
So let's bring him.
Yeah, that would be great.
Yeah. And the relevance of that topic for us is, we are using embeddings for search and retrieval problem, which is largely an unsupervised problem. But then we start, when people use our platform, we start seeing feedback from them. So how now to incorporate that feedback into these embeddings? You can, of course, think about simpler ways to do it. But what are the most efficient ways to essentially turn an unsupervised problem to a supervised problem, essentially provide context, provide known context that are not necessarily labels to your data set so that you can improve your embeddings so that the unsupervised problem becomes more efficient at producing whatever it is producing. I'm sure there's research on all the above, as you audience will find and let us know. On that topic, shall we close it?
Yeah, I think that sounds good.
Great. All right, Serena, thank you. I learned a lot from you today.
Same here.
I'm looking forward
from myself. Just kidding. I learned from you.
Looking forward to our chat in 2 weeks. Did we decide what that's about? I don't remember.
It might be data augmentation, or it'll be some sort of new Facebook algorithm, I think.
Oh, right. No. It is the DeepMind alpha code.
Okay.
That we are going to talk about in 2 weeks with two of our very good NLP people. So next time it's not going to be as guessy as today was, hopefully. Yes. But yeah, hopefully you'll learn something too and come back next week that we will talk about some machine learning product related thing that I don't remember. Sorry.
You're doing a very good job of selling people on it.
This is informal. I don't think we have decided on the topic and exact topic. I know we have engaged a guest, but the topic is still TBD. But it will be related to machine learning products and user experience research and how these interact, etc. Roxana will be the co-host there. And hopefully you can join us for that conversation too. And hopefully you can learn something and we can learn something from you. Thank you so much, and we'll see you later. Make sure you subscribe to my channel and give a like to this video.